with your topic.
Hello, good afternoon. Thank you, Martin, for introduction. Today, I want to talk about, in this session, about the high voltage applications and what are the difficulties when it comes having the high voltages in your application. My name is Royan Nikju. I have PhD in electrical engineering and I'm based in Stockholm, Sweden. I have also some years of working experience in industry and research at university. And I have been with KEMET almost 2 years since 2019 as a field application engineer. Today, we're going to talk about what do we consider actually high voltage, talking about the MLCC ceramic surface arcing and the complication that it causes, and what KEMET can offer as an arc shield series regarding these kind of problems. Then what we have on the other types of high voltage ceramic portfolio. Then I will talk also about some designs that we consider in the film capacitors regarding the high voltages and also the failure modes that it can happen. When it comes to the high voltage application, we need high voltages, when especially we need the high power. So either we have to go through the high capacitance and high voltages to be able to reach the high power. But there, as we have different technologies for different capacitors as we have, the main two capacitor technology that can be used up to higher voltages are the film capacitors and the MLCC or multi-layer ceramics. So because of that, I focus mainly on these two technology and our design is specifically to handle high voltages. So as we have different applications for high voltage, as I said, when we need high power, like in the energy sector, automotive, industrial, or even at the consumer point of view, so we need to go for the in our design to the higher voltages. When it comes to the DC links, when it comes to the filters, the snubbers, power factor connection, and the coupling. So these are the applications that then we need to use the components which are also designed for the high voltage applications. When it comes to the ceramic capacitors, what now we also can consider, because high voltage can have different meanings in different contexts. Here I consider like the voltage above 250 DC or AC when it comes to the voltages for the passive component or the capacitor. When it comes to the MLCC, one of the issues, because also the trend is going to the smaller and smaller case sizes, but we need to consider that, of course, we are limited by the fact that having higher voltages maybe is not possible when we go to the smaller chips of the MLCCs, especially when it comes to the environment that has high humidity, high surface contamination, and considering the decreepage distance, we need to keep in mind that even if the component is designed to handle that voltage levels, especially the environment parameters such as these can affect the fact to have, for example, surface arcing. Surface arcing can happen, is an electrical breakdown can happen between the two MLCC terminations or between the termination and the internal electrode of the ceramic body. If we look at the surface arcing failure modes that can happen to terminal arcing, as you can see here, we can see the carbon traces of this type of arcing happening between the two electrodes, or if it comes to the voltage breakdown failures, that we can have a terminal to the active arcing from the terminal to the first internal layer of the MLCC. But when it comes to this type of phenomenon, we consider two things, or they have two different definitions as well for the creepage and the clearance. So we call creepage is the spacing between the conductive elements through an insulating surface. And the clearance is the space between the conductive elements through the air. And we know that the air has much lower insulation capability and breakdown. So we always design the components that can handle these clearances. And also, but of course, like here, it can be creepage larger, but in the other components, they can be similar to the clearance. But the components is designed and consider the fact that it should be able to handle the spacing of the clearance that it has in the air, and it won't have a breakdown. When it comes to the MLCC assembly parts, we can see that the creepage and the clearance are almost the same. They can be a little bit, the creepage larger if you consider some micrometers here, but they are almost the same. When it comes to the surface arcing, and when you connect the part to the mains, to the voltage source, we can have an opposing termination. And as you can see, the connections of the layers to the terminations, we have also alternating layers creating opposing electrodes. And if there would be any, for example, failure or weak point in the insulation in between, we can have even like the internal arcing of the layers as well. But when it comes to the surface arcing, we can explain that it can happen like this. When we have the opposing electrodes and we have the electric field and their first layers, as you can see here, having first counter electrode, when it comes to the opposing termination with the opposite charge, we have the higher intensity of the electric field here between this termination and the first counter electrode. So because of that, this point can be our weakest point when it comes to the surface arcing. But it's not only that, because we have the electric field here that is caused by the terminations and different charges on our electrodes. We have the ionization of air as well. This electric field can ionize the air. Because of that, if you have more moisture in there or even more contamination, this can get worse and you get more ions in the surface of the MLCC. And then these ions and this electric field can cause the electric arcing if it gets enough charge on top. So then it comes to the surface arcing that you can see the trace of carbon on the surface of the MLCCs. And this can happen when with the inception voltage below the rated voltage. So this phenomena can happen even below the rated voltage. Because of that, you need to consider if you are using the part and then you have the very humid or contaminated environment, you can think about the risk of arcing that you have. And one thing that you can actually try to avoid it is try to using a part that had a bigger clearance. This is one way, and also in this way you can increase the also like considering with the rated voltage of the capacitor, also choosing a part number which has a higher voltage rated and higher clearance. So surface arcing, as I mentioned, can happen between MLCC termination or between the termination and internal electrode structure, specifically the first counter electrode. But what we have for the solution for the MLCC surface arcing? So we have like surface coating. This can be done by the suppliers through the additional process step. Critical, but it gets critical if there would be any damage to the surface coating. So because of that, also we have other solutions as well, but also it can be done through the PCB coating as well, through also that can be added to the PCB assembly and additional process step, or also added cost. So the other way is through the serial electrode design. As you can see here, when we have two series parts inside the MLCC design, we reduce the electric field strength through this way. But in this way, we have two series capacitance. So we reduce the capacitance capability inside the same size of the MLCC. But it allows us for the higher voltage capability and even reduces the probability of having failure due to the flex crack. So for example, if we have a crack in one side, still we kept saved the other side and we don't lose the capacitance. But we have also the third solution as well, which we call it the arc shield design. In the arc shield design, we have the special design for the first electrodes. And then through this, we reduce the electric field strength, reduce the ionization of the air at MLCC surface by reducing the electric fields on the surface. And through this, we maximize available capacitance in the MLCC package size, because here we don't need to reduce the area that we have the capacitance as much as the serial connector. And in the arc shield also, we increase the distance between the layers as well for the higher safety. So when it comes to the coating, as we've mentioned for the first solution, when it comes to the coating, also it gives us the possibility to have less ionization of air on the surface, and by keeping also the same creep edge distance. And it helps us to avoid having the surface arcing. But if there would be any damage in the coating, that is the challenging part for that. And then we can also have the, again, electrical arcing and having the high concentration of the ionization. And then the arcing can happen between the electrode and the damaged part of the coating. So it's so this is the cons with when it comes to the coating, so that there shouldn't be any damage in the coating, and if it happens, it won't protect your part anymore. When it comes to the serial electrode design, as we have, or sometimes we call it even floating electrode design, we have two parts, active parts in series, and there is a separation between the series elements. And as I mentioned, like through this, we are reducing like the electric field that we have and on each active part that we are inside, but also because they are in series, the combination of them having lower capacitances. So we cannot use the whole area to provide the high capacitance. But also it helps us to have a bit other safety when it comes to the cracking, because if there would be cracking in one active part, we save the other part, and it helps for the higher reliability. When it comes to the serial design and the shell design, as I mentioned, in the serial design, we can even have the possibility to have more than 2 sections. So if we have even more than 2 sections and while making them in series, so we can make it possible to get to the higher voltages, but at the same time reducing the capacitance, the total capacitance 1 over C, and like according to the number of sections that we have. But in the shell design that we have, so we have still can keep the large area of the overlapping between the layers, so we don't compromise the area, but also increase the thickness between the layer, which also can affect and decrease the capacitance a little bit, and to be able to have a higher reliability when it comes to the arcing. But still, this can provide us higher capacitance in the same area compared to the serial design. So because of that, we have introduced our arc shell technology series, which we in the arc shell series, we have the electrodes, the first electrodes connected like this. So we have half connected to one termination and half to the other. And as you can see here, this will be the distribution of electric field on the surface. So we won't have like a high density of electric field on one corner. In this way, another explanation in the reduction of electric field is that we have the opposite field extend close to the terminal of opposite polarity. So we have a low energy barriers, but in the arc design, when it comes to the terminal to terminal arcing, we have opposite field with the longer distance from the opposite field longer distance from the terminal of the opposite polarity, and in this case we increase the size of the energy barrier. So considering the standard design, in a standard design of the, for example, X7R MLCCs, there are three ways that we can fail when it comes to the high voltage. We can have an arcing between the terminal and the first electrode of opposite polarity. We can have arcing between the terminals, or we can have the internal breakdown between the layers. When it comes to the arc shield design, we add a shield to prevent the prevent the arcing between the termination and the first electrode, because we increase the distance, and then the shield also creates a barrier in between, so avoiding the arcing between the two terminals. And we also use the thicker active parts between the layers inside to increase the breakdown voltage between the layers. So through this, we can avoid to have the arcing that can happen in case of the problems. This is a patented electrode design that we have at KEMET. It is a permanent protection for the, when it comes to the high voltages. In our series that we offer, we use X7R dielectric. The voltage levels that we offer is 500, 630, and 1000 volt, and up to 560 nanofarad. And we have also the flexible termination available for this series. But as I want to mention, though, our high voltage products are not just limited to the arc shield one. Arc shield one is when you have a condition that you can have the possibility to have the arcs on the surface or more failure because of your environment as well, and you want to avoid it with all the possible way. But we have also a lot of high voltage products, SMDs like up to 10K for when it comes to MLCCs, KPS series, and also through hole series, pulse discharge, Goldmax, KC-Link, KPS, and arc shield, as I mentioned. But as when I want to emphasize that when it comes to the high voltage, you need to consider that you need enough, that you need to not only look at the rated voltage, but of course, like when it comes to the impulses and other condition when it comes to your environment and what can be the situation generally for your capacitance. So it's not recommended that you always go for the smallest MLCC that you find and you just look at the rated voltage. So it's not enough to ensure the reliability of your component in your design application. We have also another thing when it comes to the protection, and it is also for the ESD sources. So when we have like the electrostatic discharges, we can also get like a huge impulse coming and go through like connected to our ICs or something. But if we want to protect our ICs, we usually use MLCC in parallel to be able to reduce this voltage to the smaller. But the standard MLCCs are not like tested for the ESD, like for the electrostatistical discharges. But we have the ESD rated also standard ESD rated MLCCs, which have an optimum design to meet the highest ESD rating. and the designs are controlled to maintain the ESD rating through the whole life cycle of the part numbers, which you need to consider the standard ones, if they might change or something, and it's not mentioning what will be the ESD performance. And also considering the fact that these ESD specific series, every batch tested for ESD and compared to coding, because also electrostatic discharges is another phenomenon that can destroy even like your circuits, and you need to protect it, and it is more recommended to use the ESD parts which are tested to handle such a high transience. So after MLCC parts, it's good also to talk about the film capacitors and our special designs when it comes to the high voltage capacitors. When it comes to the film metallization, we have different type of metallization in our designs. So in the old metallization, we use just a flat metallization on the polymers that we have, for example, polypropylene and those. But in the modern one, we use the heavy edge, usually using zinc to be able to reach the high dV over dt or the current peak, for example, like in stubber applications. But even we have the wide heavy edges like this that are designed for the DC application. It's a mix of the zinc and aluminum. And also we have the slope profile, which are also used for the new design of AC and DC applications, and zinc for the AC, the mix of zinc and aluminum for the DC application. But the DC performance is better when it comes to with this slope. It's better than wide heavy edge, but also can be less stable. But I want to mention that you need, if you are using our products in the old design, please consider using the new design, because we are all the time looking for new and improvement of the technology and design to be able to reduce the failure and increase the reliability as much as possible. When it comes to the metallization, and as I showed here in the slope profile that we have, the parts that having the lower metallization thickness, having better self-healing properties, because you know that when it comes to film capacitance, polypropylene is one of the important factors. These parts can have a better self-healing, but higher ESR and higher current, lower current capability. But the thick parts, as you can see here, it has a lower metallization resistance, lower ESR, but worse self-healing, and have a high current capability. But with the combination of these both, we are able to provide the performance that you need for your application. But you need to consider that what are the failure modes to consider when it comes to the high voltage. These failure modes that I'm mentioning here are just from the effect of the high voltage I'm mentioning, but it's not only limited to that. We can have the failure regarding the temperature, regarding the current that you have, but this I'm specifically talking about the high voltage. So if you apply the voltage that is higher than the rated voltage of the capacitor, in this case, you age the film capacitor and increase the life and decrease the lifetime. For example, if you are using the cap at 85 degrees, 0.78 times of the rated voltage, your capacitance loss to be in the end of the life that we consider 2% loss can happen after 100,000 hours. But if you use that capacitance at 1.4 times of the rated voltage, this end of life can happen after 1,000 hours. So how important it is to choose the capacitors according to your applied voltage and consider to have a right margin when it comes to the voltage to avoid to age your film capacitors and reduce the lifetime. Also the same when it comes to the AC ripple over voltage and exceeding the VACA specification. So we can have an electro erosion at the edge of metallization or partial discharge exceeding the or we have a partial discharge, and it also can cause a rapid capacitance loss. So we will have an increased ESR and also a decrease in the capacitance if you use the AC ripple over voltages exceeding the specification. Another thing is the over voltages. We have also like a limit for the over voltages when you have it on the data sheets. So if the over voltage exceeds the surge voltage specification, the same you can have a capacitance loss due to the erosion, as we mentioned regarding when if the applied voltage is larger than rated voltage, but also we can have an arcing discharge across the metallization layer, which can cause also capacitance loss. Different phenomena can happen. We can have a loss of metallization that stop the arcing, or we can have a continued arcing and a chimney effect happens. Or if we have a segmented film design, the fuses can open up and we have the capacitance loss. Or we can have the short circuit due to the internal insulation breakdown, and we can get the carbonized burn at the winding edge. This can also include the damage to the surrounding of the resonant capacitor area. So this is so important to also when it comes to the over voltages, and specifically don't consider, okay, we are allowed to have, for example, 1.5 times of the voltage rated at the transients. But of course, you cannot expose the capacitors to so many transients. It's just limited. And if you have the application that all the time it's going to get exposed to the over voltages, so you can also kill the capacitors through this phenomenon that can happen. As you can see here, for example, this is a film pair on wound from new capacitors. So this is how it looks like. But when we have an erosion or partial discharges, you can see this film with metallized film can become like this. So we have just the metal part here, but no metal part on the edges. So by time the metal part gets eroded and then getting smaller and smaller, and we can also in this way reducing the capacitance. This can happen at low temperature. So it is not necessarily dependent on temperature, this phenomenon. It requires also inception voltage. Like for example, if you have the partial discharges, can happen at a specific voltage, and this can be below the rated voltage happening as well. And it happens when we have a localized high electric field, especially like, for example, metallization edges. We have the higher electric field there, so it can happen that we have partial discharges there. So this phenomena can be controlled with the film thickness, moisture barrier, and proper production process. So we are aware that this kind of failure can happen for the film capacitors. So we are designing and improving the design by choosing the right thickness, moisture barrier, and proper production process. And we can have also electrochemical corrosion. This can happen also through the air gap induced voltages. So this reaction is also driven by the applied voltage. As you can see here, again, we have the metal parts and the areas which are without the metal, which are getting corroded. So, and this corrosion rate is directly proportional to temperature, humidity, and the DC bias. So, but as again, we are aware of these kind of phenomena can happen, and we are fixing by selecting a special material and setting up a special production process. When we look at the polypropylene film magnified under microscope, we can see that it is not perfectly plain. So it causes that there will be some, when we are doing the winding process, the ambient air can get caught in the film winding. So air inside the film windings are the main cause for the partial discharge effect, electrochemical corrosion, and oxidation of film surface metallization. But with the new production process and material, we focus mainly on the air content reduction and moisture absorption in the wound element. So we are aware that these problems can exist, and we are trying with the new technologies and the new design to remove the air contact as much as possible and also reduce the moisture absorption. But we are not only limited to the polypropylene film capacitors or other polymer film. We have also the paper film, metallized paper film capacitors. These are having higher partial discharge resistance compared to the other film capacitors because we use the epoxy impregnations of the metallized film capacitors to eliminate microcavities and voids that can cause a partial discharge, and also it can increase the inception voltage of partial discharge and the capacitor's rated voltage. So specifically, when it comes to their application that they have quite high transient voltages, we offer and we really suggest that you go for the paper metallized film capacitors, that they have a high resistivity toward partial discharge and high reliability. So you need to choose your part according to your application, according to your condition that you are using, and always don't hesitate to discuss and get advice from us, from the suppliers, because we know which kind of series or which design can suit which kind of applications. So please use us and for choosing right components for your application. Another application that actually uses quite a high voltage parts is like a snubber application that you already seen in other sessions. And the typical rated voltages is like 1,200 volt to 3,000 volt DC, and it demands quite a high life expectancy. Is the capacitor that are connected in parallel to the IGBTs, to the semiconductors, to damp the dangerous voltage spikes. And the most important parameter in these numbers is the high dV over dt, or the peak current. So for this, we also have a special design when it comes to pulse and resonance. Because of that, we don't suggest that you just go and pick up any capacitor that you want. It's so important that go for the special capacitor that are designed for this pulse and resonance application. We have either single metallization in parallel or in series, even for to reduce the electric field, increase the reliability when it comes to the high voltages, or when we demand a higher current, you have the double metallization designs in parallel or in series, as you can see here, or we have the film foil parallel or series, and the film foil we use the metal foil. And in this case, we are also being able to increase the dV over dt much higher. So just to mention that we have the designs specific for different applications, and we consider all the difficulties and all the problem that these kind of capacitors should handle, and we adapt our design and technology to avoid the problems as much as possible. For the AC filter applications, for example, we have also used thicker metallization in the contact areas, and we have also thicker metallization in active, thinner in the active areas for the self-healing. We optimize the active area, and in this design, we have less partial discharge or corona effects when we have also the thicker metallization in the contact area. And beside that, we also work on the segmentations. Segmentations also is done like total capacitance divided to so many elementary cells protected by the fuse gates, as you can see here. So in case there would be a weak insulation point in somewhere, only that cell will be removed through the fuse activation. So you won't lose the whole capacitance. It won't affect the rest of the capacitance, only that a small part can be. But of course, your capacitance will be reduced according to the surface that you lose, or as a function of the cell element fuse activation. And the last will be like also DC link capacitors. And we also have for them, for the application, welder, solar converters, wind motor drive, and onboard battery chargers. We are going to having higher powers, so higher voltages as well. But as to mention, for the DC application, the partial discharge phenomena usually happens at a higher voltage, and also the insulation materials can handle higher DC voltage. But still, for each design, like if we have the specific capacitors for the DC application, DC link, it means that we are designing them that can handle those voltage and those electric field condition to be able to provide the most reliable performance. So we really recommend that you choose the capacitors according to the application that you want, and the series that are related to those, because each requires to have a special designs to be able to avoid failures that can be caused by, for example, high voltages. So I'm done with this, and I'm open